Hello students, in this video lecture I am going to discuss about how addressing is handled in paging. Before we discuss that, let us try to recall the basic idea of paging. Paging is basically a memory management scheme. The primary advantage of paging is that it eliminates the need for loading processes into contiguous memory locations. So before paging, a process has to be loaded entirely into a memory block, and we have to always find a single large memory block to accommodate a process. But with the paging, it's no longer necessary, because in paging a process is divided into equal sized partitions called pages. Similarly, the main memory is also divided into similar sized partitions which are called frames, and in this arrangement, loading a process into memory simply means that you just have to identify a number of frames that are equivalent to the number of pages which needs to be loaded at the given moment. So if you have to load 10 pages, then you just need to identify 10 frames in the memory, and the 10 frames may be in any order. It need not be in exact order. They can be in random order also, but we will be having the page tables to map the page numbers with the frame numbers. So this is the idea of the paging. Under the paged implementation, whenever the CPU executes a process, the process will supply some address. So every instruction comprises of an address, and the instruction either points to the memory location where the next instruction is present, or it points to the data that is required for the current execution. So if let's say there is a program counter which contains the address, we know that program counter always points to the next instruction to be executed. So when this value is submitted to the CPU, it forwards that address to the memory management unit, and the memory management unit is supposed to use that address and fetch the instruction from the memory and forward it to the CPU. And so in this case, what happens is that the address that is submitted by the CPU to the MMU is not the actual address, but it is a virtual address. We will explore the difference between virtual address and physical address under paging and how it is mapped. So basically, the CPU only submits the virtual address to the MMU, and it is the task of the MMU to convert the virtual address into physical address, and that is where it is going to utilize the page table. So in order to understand the idea of the virtual address, which comprises of a page number and the offset, okay, so here it is mentioned that the virtual address comprises of page number and offset. So the question is that why do we need two values? Why we have to split every address into two parts, page number and offset? Before I actually explain you that, I would just like you to understand the basic idea through this simple example. Let us assume that some delivery has to take place to one of the houses in this particular apartment. So let's take that there is a Zomato delivery which needs to be delivered to a particular home. Let us assume that that particular home is here. So how the delivery person will exactly deliver that particular item to the owner? He has to know two details or two addresses. Number one, a particular block. Let us assume each one of these building is considered as a block. So he has to know in which particular block the required house is located. So this is a larger address. After that, he has to know the door number of the specific house. So with these two values, he can complete his task. So similarly, this is considered like a page. So a page is a larger entity which comprises of several bytes, and the CPU actually wants a particular byte within that page, and that is what the offset value. So the page number identifies the larger memory region, and the offset identifies the specific byte within that particular memory region, and that is the purpose of having both the page number and offset. So a single page comprises of multiple bytes, and whenever CPU sends an address, it actually wants a particular byte to be retrieved, and it is not going to need the entire page. it is only going to require 1 byte from that particular page. So the effective physical address should consist of the frame number and the offset. So offset is the particular byte address within the frame number. So the CPU supplies the page number along with the offset, and the page number is then replaced by frame number with the help of the MMU and the page table, and then it forms the physical address as frame number and offset, and then it is used for retrieving the actual data from the memory. This is what the overall idea of paging. So it is like this. If you say that a frame is of 1 KB, what you actually mean is that it has got 1024 bytes. So when you say a single frame is having, or single page or single frame is having 1 KB, we actually mean that there are 1024 bytes. So if you want to retrieve a particular byte, then you have to specify the byte address. Just specifying the frame address is insufficient. You also have to specify the specific byte address, and that is what is facilitated through offset. So every address generated by the CPU is going to be divided into two parts, page number and offset, and the page number is used in the as an index into the page table, and that is because the page number is used to relate the page frame number. So with the help of the page number, we are going to identify the frame number, and the page table contains the base address, or in other words the frame number with respect to the physical memory. So we actually need to know the frame number which is actually the address of the physical memory, and after that it can be combined with the offset, which we have already discussed. And this is the overall arrangement. So whenever you are having a paged memory management system, then you have got a large virtual address space, okay, which is split into a number of pages, and then there is a program running which is supplying some address, and that address is typically a virtual address which comprises of two parts, page number and offset, and without realizing any of this, the CPU simply forward it to the MMU. The CPU has no responsibility of knowing which is page number and which is offset. It just has to send it to the MMU. It is the MMU which has to separate the page number and offset and use the page number into the page table to fetch the frame number from the respective index, and then combine it with the offset that was already there, and then it can identify the physical address. And once it knows the physical address, what is left is just go to that address and retrieve that byte from that particular address and send it back to the CPU, and then the program will continue to run with the help of that particular data or instruction. This is the overall cycle of the page translation in under paging. So this is an example. Assume that the logical memory size is 64 bytes. So what do you mean by logical memory size is that, or what do you mean by logical memory is that logical memory is the collection of pages pertaining to all the processes that are currently running in the system. So if there are some 10 processes currently running, and if each process comprises of 5 pages, then totally we have got 50 pages in logical address space. So logical address space is just a collection of all the pages pertaining to the processes that are currently running. But the point is that not all the pages are loaded into the main memory. We have already seen that the advantage of paging is you don't need to load an entire process into main memory. Say for example, if a process has got 5 pages, you can load 3 pages into main memory and 2 pages into the virtual memory, secondary memory or virtual memory. So you can selectively load some pages of the process into main memory and some can be kept in the secondary memory. So in this way, we don't load any process entirely into the main memory, and as a result, the logical memory size would be typically much larger than the physical memory, because physical memory is going to be the size of the main memory, and that is limited. But virtually, because we are combining the virtual memory and the physical memory, the logical memory space looks very large comparing to the physical memory space. So in this case it is said to be 64 bytes. 64 bytes is actually equivalent to 2 power 6. So each and 2 power 6 means that we are going to have 6 pages. So there are going to be 6 pages in the memory, and the page size is also okay. The page size is said to be 16 bytes. Okay. So since the page size is 16 bytes and the total logical memory space is 64, the number of pages that are going to be present is 64 divided by 16. So this is the correct result. So given 64 is the total memory size and which is split into pages of 16 bytes, eventually we are going to have 4 pages, and that's what you can see here: page 0, page 1, page 2, page 3, and within each page we have got 16 bytes, that is already given. So 16 bytes are going to be comprising of each page. So the address of the first byte will be 0000 and the address of the last byte will be 1111, and in this way you can see that in each page we have got 16 bytes. And now when there is an address submitted, it has the page number along with the offset. First the page number is used, then there is a page table. Assume that the page table is having some address. After that the page number is no longer needed. Once the frame number is found, then we don't need the page number anymore. The page number is replaced by the frame number, and the offset is simply carry forwarded. So 1100 is the actual byte address, and there is a frame number which will be identified with the help of the page table, and then these two forms the physical address. And we are going to look at different aspects of this scheme. First point is number of address bits required. How many address bits are required? So for a given memory size, this is determined based on the size of the memory. So how much of memory to be addressed is what used to calculate the number of bits. For example, if you are said that 256 MB of memory needs to be addressed, then it actually has got these many bytes. And remember that memory is all typically byte addressed. So each byte will have to have unique address. So if you are asked to say how many addresses are needed for an memory, you just have to convert that memory size into number of bytes, and that is just the answer. See, if there are 200 bytes in a memory, then you need 200 addresses, so that each byte can be given unique address. And in this case we have calculated the number of bytes to be 268435456, and that many addresses are also needed. So that is what the answer. And okay, now then how do you express this in 2 power? This is the number of bytes to be addressed. Then how many bits are needed? The final answer is number of bits. For that the answer is 2 power 28. That is simply because 2 power 28 is equal to the number of bytes we have calculated. As a result, we need minimum 28 bits to uniquely identify each of these bytes. So the final answer for the question asked is that 28 bits are necessary to address memory of 256 MB. And already we have addressed the difference between logical memory and physical memory. So logical memory is equivalent to the sum of all the pages of processes that are currently running, whereas physical memory is a real memory. It is the actual main memory. Size of the main memory is the physical memory, and physical memory is always less than the logical memory. Therefore logical memory is greater than the physical address. Okay, logical address is greater than the physical address. Okay, next one is page size. So the page size, how do you calculate the page size? The page size is generally determined by the hardware. So the hardware, how much of memory is there, physically how much of main memory is there, accordingly the page size is computed. But normally it is in the range of 512 bytes to 16 MB per page. This is a standard size. The size varies between 512 and 16 MB. And the selection of all we always choose the size to be 2 power. So that we can express the value in 2 power. This makes the translation easier. That is, you can easily split the address into 2 parts, page number and offset, whenever the address is represented in power of 2. We will see a lot of examples for that. If the size of logical address space is 2 power m and page size is 2 power n, then you can have the address in size in this way. So the first part of address, that is m minus n bits, will be used to represent the page number, and the remaining n bits will be used to represent the offset. So we will be splitting the address into page number and displacement or offset, and this is how it is done. Okay, let us now take an actual example. So we have a computer that generates 16-bit addresses. So that means that we can go for a maximum of 64 KB memory. We are taking a sample example. So 64 KB is too small for any computer, but just for the sake of discussion, we are treating that there is a computer which has the maximum of 64 KB memory. So for such computer, the address bits will be 16, just because 2 power 16 is equivalent to 64 KB. And this is the virtual or logical address space. And now assume that the page size is said to be 4 KB, which means it's comprising of 4096 bytes. So we need 2 power 12 bits to represent the page, so pages. So that is because 2 power 12 is equivalent to 4 KB. Okay, for each byte, so see, if there are 4096 bytes available in each page, then we need 2 power 12, that is 12 bits to uniquely identify each of the 4096 bytes. How 12 is arrived? Simply 2 power 12 is equivalent to 4096. So in order to represent 4096 bytes with unique addresses, you need 12 bits. That is what the calculation. Then we have got 16 pages. How 16 pages? Because one page size is 4 KB and we have got 64 KB of memory, which means 64 divided by 4 is equivalent to 16 pages. So the total page is divided into 16 pages because each page is of 4 KB. And 2 power 4, so 4 bits are needed to uniquely identify each one of the 16 pages, simply because 2 power 4 equal to 16. And this computer, okay, now this is all about logical. So we have been calculating the logical address size. So 64 KB is the total logical address size and 4 KB is the size of a page, and as a result we were able to calculate that there are going to be 16 pages and we need 4 bits to uniquely identify each page and 12 bits to uniquely identify each one of the 4096 bytes inside the 4 pages. Now regarding the physical address. So there are 32 KB of physical memory in the computer. Once again you can see that the size of physical memory is much smaller than the logical memory. Then we can also, okay, and this computer has got 32 KB of physical memory, which is equivalent to 32,768 bytes, starting from 0 to 32,767, and that means we need 15 bits. So 15 bits is 2 power 15 is equivalent to 32,768. So in order to uniquely identify the main memory, we need 2 power 15 bits. And once again you can see that the size of the logical address is going to be 16, whereas the size of the physical address is comparatively smaller. It only needs 15 bits. After that we can say there are 8 frames. How 8 frames? 32 KB is a total number of main memory, and we have already seen page size to be 4 KB, and page size is equivalent to frame size. So we don't need to expect a separate value for that. So 32 divided by 4 is 8 frames. So for that we need 3 bits. So for representing 8 frames we need 3 bits, and that means that we could load maximum of 8 pages into the memory, because there are only 8 frames. Out of the 16 pages you can only load 8 of them into the main memory at a time. and after that you have to replace them, and the remaining pages will be kept in the secondary memory or the virtual memory. And this is what it results in. So the address actually is going to comprise of 16 bits. 16 bits because 12 plus 4. See, the actual address is determined based on the logical address space, not physical address space. So our address size will always be is going to be the logical address space. So we need 12 bits for offset and 4 bits for page number, which is going to be like page number. The first 4 bits are going to be used to identify the page number, and the remaining 12 bits are going to be used to identify the offset within the 12 bits, offset within the pages. And you can also see that it exactly match with our given values. 2 power 4 equal to 16 pages and 2 power 12 equal to 4096 bytes. So totally there are going to be 16 into 4096 amount of memory. Whereas when it comes to physical memory, we just need 15 bits, one less than so there is no change in the offset. Offset is going to be equivalent between logical memory and physical memory. Only the frame size and page size will differ. So here we need 4 bits, but here we need only 3 bits. That is because the number of frames are only 8. So we just need 3 bits for representing the 8 frames. We are now going to take a sample problem. The problem is, given that the logical memory is 64 MB and the physical memory is 32 MB, page size is 4 KB, compute the size of the address, size of the page number and offset. So here we have got 64 KB of physical memory. Step 1, for 64 MB of logical memory, how many bits are needed? That is the first question we have to answer. So 64 MB is said to be the physical memory, and we know that memory is byte addressed. So how many bits are needed? It needs 26 bits. Since 2 power 16, 26 is equal to 64 MB. You just try to calculate the number of bytes equal to 64, and it will be exactly equal to 2 power 26. So we need 26 bits as the logical address size. We got first point, and then the given value is page size is 4 KB, which means that the number of pages that are going to be available for 64 MB is we convert 64 MB into KB, which is 65536, and divided by 4 because each page size is 4 KB. So we compute that it is going to be 16,384. Now the next value we have to calculate is how many bits are needed to represent these many pages. Once again it has to be a 2 power value. So we compute that it is 14 bits because 2 power 14 is equivalent to 16,384. So we have got the logical address size. Totally 26 address bits are needed, and out of which 14 bits will be used for identifying the page number, and remaining, that is 12 bits, will be used to identify the offset. We already have seen that for 4 KB it needs 4096 bytes, and that requires 12 bits. So once again we will see it here. Since each page comprises of 4 KB, it needs 12 bits to identify each byte in 4 KB, which means 2 power 12 equal to 4 KB. So the logical address size is nothing but 14 plus 12, which is equal to 26 bits. That's what. So we in one step we calculate the total address size, but we just have to calculate the split. How many bits are to be used for pages and how many bits are to be used for offset, and that is what we have done in the remaining steps. Now what is left is calculation of the physical address. Since the frame size is said to be 4 KB, that is same as page size, so it is also 4 KB. And how many what is the memory size given? Physical memory is 32 MB. So we have to convert this into number of bytes and divide it by or we have to just divide the 32 MB into number of kilobytes and then divide it by 4, which results in 8192 frames. So 32768 is actually the number of KB equivalent to these many MB, that is 32 MB, and dividing it 4 results in 8132. Then how many bits are used required for that? 13 bits, because 2 power 13 equal to 8192. So the physical address size is 13 plus 12, which is 25 bits. So we have calculated both parts of the answer. The first part is logical address 26 bits, and this part is page number, and this part is for offset. Similarly, for physical address, 13 bits are used for frame number, 12 bits are used for offset. Offset will always be same between logical and physical address. This is the final answer we have calculated. And sometimes the question may be asked if in decimal level. So like this is a question taken from your textbook. So in this case you are given a set of logical memory and physical memory, and different pages are loaded into different frames. You can see that they are not in any order, randomly loaded. So you have to calculate the physical address pertaining to 13. So 13 is said to be the logical address, which is given in decimal value. You have to calculate the equivalent physical address with the help of the page table. I will explain the steps in next slide. To know the physical address of 13, you have to follow these steps. Step 1, find the page number pertaining to 13. How? Simply divide the given value by number of pages. Number of pages are we can see 4 pages. So since there are 4 pages, you just have to divide 13 by 4 so that we can find out the page number. So 3 is the page number, which is this particular page. Next step, locate the frame number for page 3 using the page table. So page 3 is used as an index, and we find 2 is the frame number. So frame number is found. Next we have to calculate the offset. Offset equal to address minus base address of page number. Address is nothing but the given logical address, which is 13, minus base address of page number. Page number 3, its base address is the starting address. So what is the starting address of page number 3? 12. So 12 has to be subtracted from 13. So 1 is the offset. Now we have almost got add offset with the base address of frame 2. So frame 2 is actually identified as the frame which contains the page 3, and now we know the offset. We just have to add the base address of frame 2 with the offset. What is the base address of frame 2? Refer the frame table now, and frame 2 starts at address 8, that is the base address. So you have to add 8 plus 1, okay, which is nothing but the final answer. So the physical address equivalent to 13 is nothing but 9. Let's try one more example. Physical address equal to logical address 10. First step, find the page number. 10 divided by 4, 2. Then identify the frame number that contains the page number 2. Just refer the table again. It is in frame 1. Next we have to calculate the offset. So offset is 10 minus 8. 10 is nothing but the given value, and 8 is the base address of page 2. So page 2 starting address is 8. So that's what subtracted. So 10 minus 8, 2, and 2 has to be added with the base address of frame 1, okay, frame number 1, which is 4. So 4 plus 1, okay, 4 plus 2 is the final answer. So the address physical address equivalent to the logical address 10 is nothing but 6. So you may also be asked this kind of question, and so that is what the idea of the addressing under paging. So to summarize, what we have discussed is that the basics of paging, and after that we have discussed about how to calculate the number of address bits needed for a given address, a given memory size, and then how to split that address bits into number of bits for page number and number of bits for offset. Similarly, how to split the physical address bits into number of bits for frame number and number of bits for offset. And also, given a decimal address and the representation of the physical logical memory and physical memory along with the page table, how do you convert the logical address into physical address? So we discussed all this under this video lecture. Thank you.